Recreating the clock with machine learning and web scraping. What are we talking about? So last year, I went and I visited the Tate Modern. And at the Tate Modern was this film called The Clock. And it's a 24-hour film. Part of it being shown anywhere is that it has to actually, the museum has to be open for 24 hours itself to showcase the film in its entirety. And so the film is comprised of around 12,000 cuts from movies in popular culture. And when I went in and saw this, I was blown away, and I was super confused how they could have done this. So in my head, I was thinking, wow, did they really use like computer vision and go through, I don't know, thousands of movies and figure out where there were clocks and what the times were within it? And of course, I thought, all right, I definitely have to go back home and make the same thing. I got back home and I learned that the artist Christian Marclay actually got a grant and over $200,000 and a team of 20 people. And so they actually manually went through videos and put it into a giant Excel spreadsheet of where all the clocks were in movies and what the times were. So my idea was, how hard can this be to do, and what sort of tools will I need to do it? And so we're going to talk a little bit about that in my attempts to recreate this by scraping YouTube. So a little bit of backstory. There's almost nothing new in universal Turing machines, right? Why is machine learning suddenly a thing? And there's, multiple things coming together. But the big ones are dedicated hardware for inference. We have new dedicated forms of computation that allow us to do sort of the giant computational needs to do this. Availability of large labeled data sets. So all of your social media posts with hashtags, all of those are giving labeled data sets to be able to train on. And then there was this original gain with convolutional neural networks. So a convolution is just a fancy way of saying being able to see lines or features within an image. So kind of in my lifetime, as a kid, I heard over and over again, Go will never be solved. Go is impossibly big. It's such a giant search space that we'll never be able to do it. And so, of course, very shortly thereafter, a decade after, of being told it's impossible and it'll never happen, Google and DeepMind kind of did AlphaGo Zero, where they made this Go player play against itself, and they used a large amount of computational, when I say large, I mean extremely large, amounts of computational resources to figure out and do self-play and become a master and beat humans for the first time. Another thing that's going on is OpenAI and Dota 2. So this is kind of a bit of teamwork-based video game where they're kind of beating humans for the first time. It's some debate about whether it's being able to make moves quicker than a human, and that's kind of an unfair advantage, but still an incredibly impressive thing. And then on the lighter side, deep fakes and Nicolas Cage. Now there's entire YouTube channels dedicated to replacing every character within every movie with Nicolas Cage, and this is the future I signed up for sure. But I think kind of one of the questions, especially as an outsider, right, is how does it all work? And the hypothetical thing you hear is, it's super simple. There's 3 stages, right? You build, clean, and label a data set. You build and train a model on that data set. And then finally you deploy and evaluate, and all is well in the world. But I think the biggest question mark for most people is build a model. It feels like how to draw the owl, 2 circles, you have data, it's labeled. And then you have a model, and now it can tell the pose of every human ever. And so I wanted to showcase, this is an actual model I used for a project I will show later. It doesn't have to be too wild. It doesn't have to be too complicated. One of my favorite ways to work is to build upon other people's efforts who have already been there previously. So this model gets put on top of an open pose model to do something we'll see later. And going back to that how does it work slide, real world data is always messy and filled with garbage and a mess, and difficult to clean and label, especially on a grand scale, right? And your models tend to be brittle and opaque and difficult to debug. In the model that I'll show later, I trained it and nothing was working, and I trained it and nothing was working, and I actually mixed up my labels on my data set, and it completely broke everything. There was no way for me to be able to see that easily. And then finally, how do you measure performance once something's deployed? Do you know if you're doing things well? You kind of have to almost do sort of manual intervention to have some sort of sanity check on what you're doing. And so the machine learning development lifecycle is different from traditional development. And I think for me, one of the biggest things is suddenly the machine you're running on matters. GPUs and potentially TPUs are necessary for training on these massive data sets. One of the wilder things to me is that driver updates can hypothetically speed up your code 300%, rather than potentially slowing down your code by 20%. Yes, a few people got that reference. And as a kid, I always think, okay, what is this going to be like as a teenager? Will I be able to get into this? Will it be fun? Can I get started easily? And so looking at popular machine learning projects, it's very intimidating. So the computational needs can be staggering. How many people have heard of GPT-2 from OpenAI? So this was a language generation model that was deemed too dangerous to release. The idea being you give an input set of text, and you say, here's my input text. I want you to generate a page or two out of this input text. And so it was deemed too dangerous because it could be used to create fake social media profiles and kind of sway public opinion to any direction. But more importantly, people reproduced the paper, and it ended up costing them $50,000 worth of cloud training, which is a little intimidating for a teenager looking to get started. And this is once you already know what you're doing, right? You already know the exact model you want to build, the exact data set you're using. This isn't a sort of, I'm playing around and figuring out how to break things and eventually getting somewhere. And then I mentioned AlphaGo Zero being the thing that I never expected to be possible. There's an estimate for the cost for that around $35 million, which as a kid seems mostly out of reach. So with those training costs, there's more and more of machine learning is going to get pushed to the edge. So cell phones are all adding acceleration chips to them. If you think about doing inference, you don't want to make a trip to the cloud and back, right? If you're doing live video, you want to do all of your inference right on the machine that you have, so you can potentially do real time, 30, 60, whatever frames per second it is. And so we're kind of seeing this push to training in the cloud with these massive data sets, and then building a model and pushing it to the edge, as close to the user as possible. And with that, data sets are becoming an integral part of your code. So normally you've kind of traditionally thought in a web development, your code and your data are isolated. The way that you think about and manage your database is completely separate from your development. I mean, maybe you have migrations and you think about the structure of the database, but you don't think about the contents of the data being relevant to your code in general. And so with that, when you're building and deploying models, you also want to think about how you can use a deployed model to bootstrap even better data. So we'll see an example of that a little bit later. And so behind all of this, kind of web development itself is changing. We're seeing more and more container adoption in general. And one of the wilder things about it is that it's especially happening in larger environments and in larger organizations. So when I think of people adopting new technologies, I don't necessarily think of large companies being the first to go there and being the first to get there. And so there's this larger move to orchestration like Kubernetes. And so Kubernetes is actually what I use to do this web scraping project, because potentially I wanted to get tens of thousands of videos from places, and I wanted a way to be able to write my code and then have it deploy and scale to as big of a size as I can afford, hypothetically. And against all of that, I kind of see us all moving from managing and deploying to individual servers to pushing code to this hypothetical sea of infinite computation. And the way that we're navigating that sea is through Kubernetes. But with Kubernetes, there's definitely a trade-off. Kubernetes comes with a lot of, I'm not going to say a lot, extra complexity. So etcd is kind of the default data store for Kubernetes, and it's kind of where you put, hey, this is how everything should be within my cluster of computers. And by default, etcd and Kubernetes recommend 5 servers to maintain durability. So right out of the gate, before you even get anything set up and installed, you're looking at putting 5 servers together. And along with that, there's a growing list of sub-packages to control things like networking layers, load balancing. And it really, from the beginning, you're kind of completely rethinking development, testing, deployment, kind of as we grow beyond developing and deploying for a single dev machine. And so when I first jumped into Kubernetes, I felt like Mr. Bean on top of his car trying to steer it with, I don't even know what that is, a mop? But he's got a brush on the bottom, so that's not a real mop. And you have the one abstraction layer of Docker where you can get yourself into trouble. And then you have Kubernetes, and so those are really the only 2 things, but then you kind of have to think about how you're developing locally, so you have to understand how Minikube is different from deployment, how etcd breaks, and things just really start piling on, and you feel completely abstracted away from the thing you're trying to do. The real reason I see organizations and developers in general moving to Kubernetes and things like Kubernetes, kind of orchestration platforms, is that software development itself is growing up. We're moving away from software as a service, where you can kind of tolerate downtimes and tolerate issues, to software as a utility. Software is just becoming a fundamentally ingrained part of all of our lives. And we all rely on software that is critical to being able to do the things we need to do in our daily lives. But there's more and more pieces to manage and deploy, especially as we try to do something like machine learning within Kubernetes. And so it really just all starts to add up and be a little bit overwhelming, especially as somebody who's new. But there are a few Kubernetes native machine learning tools. Kubeflow is kind of the biggest one, and if you kind of search for Kubernetes and machine learning, it'll be the one that you pick out immediately. It's a toolkit from Google. TensorRT inference server. So we talked before about building models and deploying the models and doing inference. This is basically serverless for your models. You ship a model to the RT server, and then you can start just sending your images over, getting inference, and then getting things back. And then finally, there's things like Pachyderm, which is a platform to manage all of your data in something like source control. And so if you go and you look at the page for Kubeflow, you're going to see a lot of options. And again, for me personally, I can't comprehend or begin to comprehend something unless it's simple, unless I break it down. So that's a lot of moving pieces. And it's almost too much to even get started or just be confused, right? It's super expensive. There's a million moving pieces. Okay, this is not for me. So how do you get started? And for me, the answer is always try to do the simplest thing first. Try to do the simplest, dumbest thing you can think of first. And so for me, that was running Kubernetes locally with a GPU acceleration. And that's the best excuse to build yourself a sweet gaming PC. And definitely put a muffler on it. This is an artist, Sterling Crispin's personal computer, and definitely something to aspire to. And then installing Kubernetes, you kind of really want to run within a Linux environment, at least last I checked. And Ubuntu and NVIDIA are kind of the standard for if you want to set up your own thing and you don't want to do everything in the cloud. And it's pretty straightforward. It's a snap install micro Kubernetes. You enable the GPU. This is assuming you've already got the drivers installed. And then you can just start applying these services. And so in the early days of doing any sort of machine learning project, there was a lot of academia work, kind of building these open source libraries and pushing them out there. And they had kind of these unwieldy dependencies where you had to install a specific version of this library, a specific version of another library, and then cross your fingers and hope that all of your libraries work together and come together and you don't have to figure out where something broke along the lines. And then if you wanted to try a different library, well, that new library would completely break everything you built before, and you'd realize that you're in a state of mess. So this is an amazing resource right here. So this is a container registry. And so this is going to have pre-built Docker images that will allow you to get up and running immediately. And so this is a massive time save. Previous projects, whenever I wanted to get an environment up and running, could take me a day just to figure out which libraries to install, what versions of source control, how broken my Linux machine was from before. So definitely check this out. It's great. Here's an example of a Docker file. I know this is PyGotham, and I'm talking a lot about things that aren't Python. But these are kind of tools that will hopefully make this easier and more approachable. So here I can do this. So here I pull in the PyTorch. And so this is going to already have all of the acceleration libraries I need to be able to use my GPU. And then we clone FFmpeg, install some headers to be able to hardware accelerate things. So that's going to offload encoding and decoding of videos onto my GPU. So I'll be able to stream more data more quickly using this image. And once it's built, it's there, and it's ready to be put either on my local machine or on the cloud and go. And then I talked a little bit about Kubernetes, and it's definitely not Python. It's YAML. But it's also fairly straightforward. We have these things called volume mounts, and that's just basically a way of saying, here's a local directory on my host machine. Here's where you should put it within the container. And then there's just a bunch of environment variables we set. I put some monitoring in here. And as we move to more and more complex systems and less human understandable systems, things like observability become a necessity, right? How many people here are working with microservices in general? Okay. All right, so you've all been in hell. So it really is very difficult to manage kind of all of the change that's happening in these sort of environments. And so earlier in my career, I worked at places where I could know all of the systems that I have deployed. I could fit in my head everything that all of the software that the business relies on to build and ship things. But as we move to things like microservices, and our teams are potentially hundreds of developers all pushing at the same time, it becomes impossible for a single person to reason about the entire architecture of a system. And so this is the pipeline that I had for my original approach to recreating the clock. Okay? So I created a scraper API, which consisted of a Docker image. It downloaded and installed Firefox. It downloaded and installed a Selenium similar library to kind of manipulate and scroll the web browser. One of the things that's changed since the early 2000s is in the early days of Google, they could just scrape the entire web, right? Everything is open, everything is available. You can view and see the entire web. You could download the entire web if you had access to the computational resources. Well, now it's 2019. People are posting to YouTube and Instagram, and those places don't necessarily make it easy for you to steal their data. So you need to use things like a web browser in order to scroll through a page and find out what videos live on that page. So it's become more difficult, and the tools you need to do to still follow the terms of service for those platforms and grab their data. So you end up building things like these images and doing JavaScript to scroll through the page in order to get the list of videos. And so we use something like Beautiful Soup to extract videos, URLs, something like YouTube Download to download the videos, and then we ship it with a JSON request to an inference API. We use this model called YOLO. It's You Only Look Once. And the developer behind YOLO is a great person to follow. And then, yeah, pass it over to FFmpeg, and then extract the snippets featuring clocks. And so with that pipeline, right, if you ship code or you press a button or you start a scrape and things break, you're wondering where they broke, right? What happened? Where did it go wrong? And so distributed tracing is kind of one of those tools to be able to see in a distributed system where things are breaking. And so that allows you to get basically a graph of your request, right? Passes through your first thing, which might be a front end, and then downstream into your secondary services, and then where it hits the databases. And with the same thing, we can see the history of our machine state with metrics. So with a GPU, you want to maximize the effectiveness and squeeze as much as you can out of your memory and your resources. Using GPUs are expensive on the cloud, especially if you're not doing it locally. So you'll want to see how much memory you need for your model and maximize it. And the way you do that is with these things called daemon sets. So a daemon set is basically saying, run this container once per computer. They're called nodes in Kubernetes. And then these YAML files just get applied. In this case, I'm picking my power usage, CPU, GPU usage, and then memory usage. And kind of I can track that over time and start to see graphs of how much and whether or not I'm actually using my hardware encoder and decoder. And so sort of being able to see what's going on with a system that would otherwise be very opaque and difficult to debug. And then we kind of add the same thing with logs. Here I've started to see if I'm actually seeing any clocks, where they're going on, what's happening. Pretty straightforward. And so object detection alone begins to open up new platforms. I'm starting to think of images and video as code rather than as data. And that's kind of a bit of a transformation in the way that we think. And I don't know that we've all really understood that yet and the potential for it. And this is just speaking solely of object detection. So an example of a project that I think is very cool. I don't know how many people are confused by recycling bins. Yes. Self-sorting recycling bin, right? Use object detection to be able to tell what sort of things you're putting in the recycling bin. This is a project I did that I referred to earlier, dab and T-pose controlled lights. So we'll wait for the GIF, yes, and the light control's on and off. So that was that model that we saw at the beginning, the few lines of code, that's all it would needed. I took a bunch of photos of myself dabbing and T-posing. The data set is online if you need a data set of my dabs and T-poses for some reason. And I mentioned before about things moving to the edge. There's this new thing from NVIDIA called the Jetson Nano. It's a $99 GPU accelerated machine. It's basically a Raspberry Pi with a sweet GPU on top. And you can get started with that, and you can actually run the code that I showed before. You can get that dab and T-pose running on it. And so this is kind of part of the video from building the clock. Unfortunately, it's a GIF because presentations are difficult to do videos. And thank you.